Okay, C495. This is the video record for how to transfer all the ETABS data in order to design the foundations. Our final project, we're gonna use map foundations, supported on the rock due to the computation time effort. So here I assume that all the team, they finished the lateral load resisting system design complete, and once you finish it, I think your model is ready, so that we're gonna build the foundation elements by using the ETABS Ultimate version. So what things I'm gonna show you here, all the foundations. For the foundation design, we need all the reaction from the superstructure, right? So we're gonna go down to the base level, which is our bottom of the column and the wall. You can just double check. And all the ultimate load combination is ready. I'm turning on the vertical, the reaction due to the 1.2 depth, 1.6 live load. So you see that all the column has a vertical, the reactions. So one thing that I want to make sure, I think because for foundation design, we're gonna use a live load reductions. Let's see. Okay, this model we didn't incorporate. So I'm gonna assume for now 0.5 live load reductions. I think so. It totally depends on the tributary area and influence area. Typically the tall building column live load reduction can be achieved almost 60%. But here I'm just assume the 50% the live load reductions. So okay, and so what we're gonna do, after you complete the 3D model, what we need to do is first we need to add the map foundation, right? So I'm gonna unlock the model. So I'm gonna draw the map foundations based upon current my column joint. So I'm gonna use this because this building has a square, right? So I can draw the mat by using this rectangular 2-point, or if you don't have a rectangular symmetric geometry, you could draw this, right? So it's a graphical, I think, geometry map foundation, but the physically the column cannot sit on the edge of the mat. We need to increase obviously mat by using edit shell expansion. So I'm gonna extend maybe 5 feet. So my mat is just slightly bigger than just from our building footprint based upon the vertical column locations, right? So now this is just graphic. Since we are using ETABS, we need to adjust a couple of stuff and define the couple of stuff. First of all is the section properties, section, the slab. So for this map foundations, I'm gonna start with, let's say, maybe 9 feet. Wow. Okay. So 9 times 12. Okay, and I am gonna choose mat. Okay, we have various concrete strengths. I'm gonna choose a C6,000. So you know what? I'm gonna just make it shorter. 9 feet mat foundation with the concrete strength 6, right? So this is section properties. I'm gonna use it. So I'm gonna select. I'm gonna assign shell slab section and that 9 feet. So I'm gonna right click and see. Okay, it was assigned. Okay. Now, second thing is, since this is we didn't have any the mat previously, that means we have all the boundary condition at the bottom of the column and the wall, right? Now, since we are adding the mat, so what we're gonna do, we're gonna select all the joints, and we're gonna get rid of the boundary conditions, and then instead we're gonna assign the soil subgrade modulus. So which means we are assigning some area spring, and so let the mat foundation transfer all the superstructural load from the column and wall to the soil, right? So in order to do that, we need these properties about the soil. So this is modulus of subgrade modulus. So since we assumed our soil bearing capacity, where is it? This is equivalent to 20. It's a 10-ton soil, which is 20 ksep kips per square foot, and the modulus of subgrade modulus is 480 with the safety factor 2. This is from the geotech book typically, but we have some general average or edge condition is slightly different, but let me just choose 480 kip per cubic foot. So we're gonna go define, and where is that spring? Here, area spring, no, soil profile, and we're gonna soil profile data. Wait a minute, this is slightly different than, okay, go back to spring, area spring. Yeah, we're gonna add 480, but this is cubic foot. So spring constant unit area vertical direction. So what is this? This one, 480 divided by toe. Oh. This is inch per inch square. Okay, so 480 kip per cubic feet. So I think this is the spring constant subgrade modulus I'm gonna use for. So I'm just gonna select the area of the mat, and I'm gonna assign area shell and area spring here. So I'm gonna assign the area spring here. So you know what? Let's see. Okay. I'm gonna turn on the area spring, shell, area spring. Okay, so area spring here. And I'm gonna double check whether this mat actually is meshed. Okay, so meshed, which means all the column, right, and the wall point is somehow connected with the mesh, so that those loading is transferred to the mat and soil below, right? So okay, just confirm. And since I applied only vertical, the spring, this building or mats, it's gonna move X and Y. So I'm gonna just assign some boundary condition in X, Y direction. Only allow vertical and rotations. So let's see. So it seems like I assign all the information. So let's run the model and see. Okay, so this model ran. I'm gonna check. Okay, so the model ran. I'm just checking the soil bearing. First of all, I'm gonna set total depth plus live load. For this live load is a reduced live load, and here soil the bearing. So I turn on, and the criteria is soil bearing is 20, right? Plus minus 20. Oh. In general, you see then the soil bearing is 9.92. So I'm gonna just use 10 to 10. So it gives us the general contour, the color that soil bearing soil gonna experience about minus 9 to 7. Basically this depends on all the column and wall reactions. So this is mostly spread out through the mat and underlying soil, right? So I want you to just include this in just one of our checking procedures. Also, we need to, I'm gonna copy this, and we need to consider all the also wind, right? Wind effect. So that is a service. We always use the service load combination ASD method for soil bearing check, and in order to combine the live load and wind loads, we are allowed to reduce. This case is service live load. Okay, seems like we have a service wind load here. So I'm gonna use 0.75, 0.75. Here, interestingly, is we have to use a service live load, service wind load. Here, service wind load X. Okay. So let me see what is the service wind load. What you can see here, service wind load is with the wind speed 98 miles per hour, right? Ultimate wind load speed is 115. So in this case is we have service wind load in extraction, service Y and Y direction. How do I know it? This here, 90 degrees, the X direction here, and 0 direction. So this is applying to the X direction, and this is applying to Y direction because it's a 90 degrees direction angle. All right, so you could also create the load combinations X and Y. This case is I'm gonna create the Y directions and change service wind load Y, right? So I'm gonna also check the wind, the gravity effect will combination with the live load and wind X. So wind is blowing to the positive X, which is creating overturning effect. So on the right side, you're gonna see some more compressions, right? The left side is tension due to the wind load. So combined with the gravity effect, you see that more compression force stress is happening here, minus 11. As you can guess, Y directions, you see that wind is blowing positive Y, that the compression side is on the leeward side. You see the more soil bearing. So you need to include this part of your report. Okay, so this is the first step after we edit the math foundation and assigning all the properties. The first, the checking procedure what you're doing now here is soil bearing stress, and then we're gonna move to the stress check. Second one is, since I think as you aware of the spread footing design, what we do is we based upon the sizing the footing based upon the surface gravity load divided by allowable soil bearing capacity, means you're sizing the footing dimensions. After that, using the uniform stress, you checking the shear, two-way shear stress versus your concrete capacity, and you size the spread footing thickness. So what we're gonna do is we try to also check the shear stress. In our cases, we already have a ultimate load combinations, right? This S1, S2, and also we have a wind effect there. This is all LRFD, the ultimate load combinations. I'm gonna show you here stress. Then I'm gonna choose for now S2, which is 1.2 that 1.6 live rod. But here I'm gonna check the shear stress. Especially this is a shear in vertical. So I'm gonna turn on check the S13 or 23. I'm gonna check this. And the control value, which is based upon our concrete strength. Because of our concrete strength, we're going to use at 6,000 psi. The concrete shear capacity is for two-way shear capacity is 0.75, reduction factor times 4 times square root of F prime C, which is 232 psi is our shear capacity. So I'm going to type this, because here is a kips per square feet. So this is minimum and maximum the range. So I'm gonna turn on. So what you see, wow, so S2, wow, okay. See, this is shear stress. It quite, wait a minute, what am I looking at? Shear stress 1323, reachable phase. Shallow stress mode. Fill. Oh. No, should be PSI. Oh, so this unit I need to better change that. Should be PSI. Again, minus 232 PSI, right? Okay, so this is shear stress. Let's check it. So on this, under the core wall, we have on various shear stress. Those are all S13. So you could include this just as an example, checking the shear stress. But also this case is, since math is a two-way, so you need to check. No, sorry. This should be S13. You need to check 13 and 23 as well. So you see that which the zone has the most significant shear stress. Seems like the corner you have a significant shear, but also you could just check all the load combinations. See that? So gravity effect and combination of gravity and lateral effect, and you need to check which where is critical shear stress occurring, and we have to decide that if this is too significant, you need to start considering to increase the mat thickness. Sometimes if those forces overall excessive, then increase the mat overall. But if this is very localized shear stress, then you need to thicken that the mat and locally. So you need to check S13 and S23, okay? All right, but basically all the load combinations. All right, assume that our current mat foundation 8 feet is good enough. I use 8 feet, and we need to check design the flexural reinforcement, right? Mat design. So the next step is here. Then design, we have concrete slab design, which is we're gonna choose base because you don't want to run entire slab, and load combinations. I'm gonna use all the load ultimate load combinations for our mat design. I'm gonna run that slab design. All right, the first of all, what you're getting here, go to design and concrete slab design, display flexural design. You need to include the minimum reinforcement. I think first shot, because we didn't define any design strip, first we're gonna just use finite element base, and the contour, this is basically showing us the required rebar area of steel per unit width. So let's check the direction 1 bottom reinforcement. So this is contour, give us the number, right? So this is inches square per inches. Wow. So what I really sometimes use it. So this is the feature that I'm using, the bar instead of kind of area alone. So so I'm gonna just assume that I'm gonna use number 11 bar for top and bottom, typical uniform bar. So if I click this, and also do okay, then contour range, okay. Okay. Okay, here. So let's see. Flexural design. Okay, contour average node, okay. So this doesn't give any, oh, okay, different, slightly different. Okay, since finite element method, so we need to check the direction 1 is, which is x direction, direction 2 is y direction. We need to check all the required area of steel, inch per inches. But here, since we choose a typical bar, right, using number 11 and 12 inches, and this contour is additional bar. Here, typically, this color purple is almost 0, means you don't need additional bar. Yeah, this is actually contour range, maybe. Okay, I'm gonna switch to direction S2, direction 2. So it gives us the contour, but sometimes this finite element base contour give us the in general overview of the rebar intensity for each bottom bar and top bar. But typically I use the strip base approach, which is visually more easy to understand. Okay, so what I'm gonna do here, I'm gonna show you what next step, what we need to use. We need to draw this design strip in order to use the design strip method. So in order to do that, we need to unlock, right? And then here, we need to draw the design strip. When you click it, the strip layer A is in extraction. I'm gonna just use 5, so 60, 60. So I'm gonna draw the 10 feet wide design strip. So, right, and I'm gonna draw from left and right. The first thing you could check and checkbox, and then you could turn on the design strip width. I apply 10 feet, right? So what I'm gonna do, I'm gonna copy this all design strip so that I can cover entire mat in y direction. So I don't know how many I needed, but maybe I try to 10. Okay, I'll cover it. So this is good enough. So I cover all my mat with the design strip. So what this design strip do is usually you collecting the force, basically resultant forces within this design strip, so that we can use this shear forces and bending moment in this design strip for our shear check and also bending flexural reinforcement design. Okay, so I'm gonna also draw that the other direction, B. I'm gonna use same 10 feet. So you see that in the other direction, I'm gonna select. Now this is cases, I'm gonna copy to the X, maybe 15. Yeah, okay. So I can delete this, I don't need. Okay, so my design strip cover all entire my mat. Okay, so basically this is just design strip. I think you need to take these concrete slab classes, but basically the finite through the finite element analysis, what you're getting is all the strain and stress. What you have, we actually collecting all the shear and moment by using this design strip. So I'm gonna run the model. Let's see how fast this model run. Okay. Okay. All right. Somehow. Okay. Now this is a design strip. I'm gonna show you this strip forces. So go to the strip force and diagram and strip forces. So what we're gonna check is 1.2 stat, 1.6 live load, and then moment. Let's see how the moment diagram look like in x directions, right? And also y direction, right? So this is the moment due to the 1.2 dead, 1.6 live load. It will be used for your mat design. Obviously, we have many load combinations, right? So this is more visually kind of easy to understand. And then using, again, we run the design, slab mat design. Since we define this design strip, we could use stream method right? Extraction, I'm gonna just only show the bottom rebar. Again, I'm gonna throw out the uniform number 11 bar, and also I can choose number additional bar number 11 if I apply it. So this is actually additional bar on top of this typical uniform bar, which means I think I need additional more than this number 11, 12. So I'm gonna reduce to 6. Okay, number 11 and 6 inches is practically, considering splice, this is too dense, so that we most likely for constructability I'm gonna bundle it. So two number 11 at 12 inch on center is gonna be my consideration, and whatever just bar you show, mostly more bar under the mat concrete, right? There's also column, either I can show it additional bar or maybe I can further reduce it. But if I reduce it, means I think you over kind of provide the reinforcements to where you don't need that much. So for this example, seems like, yeah, two number 11 at 12 inch on center is my typical bar for the bottom X direction. Yeah, let's turn on the both. Yeah, Y direction as well, right? And then you can also do the top bar. Yep, typically top bar, you don't need that much actually top. Oh no, actually. Yeah, this is additional top bar. So let me see. Yeah, top bar. If I reduce it, yeah, for the top bar, also same thing. If I throw out two number 11 at 12 inch on center, this is the additional bar you needed. So that this is the only tool that's for slab design. Once you analyze it, you need to just, as a designer, will go over and figure out what kind of bar and spacing you want to throw out as a typical bar or additional bar. So you might need to play around and see what will be the most effective number of bar. And there is no such automation. This is basically the from the analysis, what you're getting is required rebar area in X and Y, bottom and top bar, but you need to just kind of play around with various bar size and spacing, and kind of throw out that required bar and with the uniform and additional bar. Okay, so why don't you just play around this, and you need to include those snapshots in X direction and Y direction, and also bottom bar and top bar separately, so that you could easily propose that you, let's say, bottom bar, right, in X direction, and then you're gonna say that you're gonna provide it two number 11 at 12 inch on center, or number 11 at 6 inch on center, and whatever just a screen you see is additional bar, you can explain that. Okay, all right, let's see. So I'm gonna just stop here. It's pretty 30 minutes, so I'm gonna just separate in the two pieces. Okay, goodbye.